Rational functions. A rational function, by definition, is a polynomial over a polynomial, which means all the exponents need to be positive whole numbers on your variables. This one here is a polynomial over a polynomial. It just happens to be a constant on top over a linear function on the bottom. This one here is a quadratic on top over a linear on the bottom. Rational functions are basically where you have variables on the top and the bottom. But rational functions behave a little bit different than most other functions that you've seen. We're going to go ahead and graph each one of these. When we graph the first one in our y equals, and remember, since you have two things in your denominator, to put that in parentheses, we will get this. When you graph the second one on your calculator, remember when you type it in, you'd have to have the whole top in parentheses and the whole bottom in parentheses. You would get this. Now, we would expect to have issues at whatever causes the bottom to be 0, and that would be at 2. You'll notice here at the left, we have an issue at x equaling 2 because we have a vertical asymptote occurring. That's just a vertical line that your graph is getting close to but never really crosses. The green graph is technically not part of your graph, or the green line is not part of your graph, but it just gets close to that on each side. Those are vertical asymptotes. Over here, you'll notice that when x is 2, we end up having a hole here in our graph. That's because you can't actually use 2. These are the two common types of issues that occur, either a vertical asymptote or a hole. Well, why do we have a hole in one and a vertical asymptote in the other? You will notice, however, for your second function, f of x, it has common factors on the top and the bottom when you factor it. So when you simplify that, it really simplifies down to just being an x plus 2, which is an equation of a line. However, we can't just say it equals x plus 2, because here you couldn't use 2, so in your simplified one you can't use 2, so we have to say that. As we are looking here, why don't they both have vertical asymptotes? Well, the second one has a hole because it has a common factor in the top and the bottom. The first one has no hole because there's no common factor in the top and the bottom that you can cancel out. So whenever you have a common factor top and bottom, you have a hole occurring wherever that denominator is 0. Here, there's nothing that we can do to simplify this, so whatever causes the bottom to be 0 is your vertical asymptote. We need to consider this here. This means as you come in closer and closer to A from the left side, so as you come in here from the left, what happens? Well, it's going up towards positive infinity, and so we're saying your function goes to positive infinity. Here, what happens as you come in from the left? Well, as you come in from the left, it goes down forever, so that means your function approaches negative infinity. When you have a little plus as afterwards, kind of in the exponent notation, that means you're coming in from the right. So as you come in here from the right-hand side, what happens? And well, it goes up forever and approaches positive infinity. Or in the bottom one down here, as you come in from the right to this line, what happens to your function? It goes down forever, approaching negative infinity. We need to go ahead and take a look at our left-handed limits and right-handed limits when we are looking at our vertical asymptotes to decide whether our graph goes up or down on one side or the other side of it. We also have horizontal asymptotes that your graph can level out at as you go far to the right and far to the left. As you go far to the right, that's what's going on when x approaches positive infinity. And here's a couple of examples of your graph leveling out as you go far to the right. It's leveling out at in this case, coming up from the underside and leveling out, but it's leveling out at a height of c. So your horizontal asymptote would be y equals c. This one here, we're still going off to the far right because x is approaching positive infinity and x goes left and right. Here you're coming down from the top and approaching that line, and it's still leveling out at a height of c. So your horizontal asymptote is y equals c. The top two up here, we're looking at what happens as you go far to the left. And that's what happens when x gets really big, but in the negative direction, meaning approaching negative infinity. And in this case, they're both leveling out at a height of y equals c. We need to go ahead and find our limits as x approaches infinity for each one of these. When you're looking at your limits as x approaches infinity, you're really only concerned about the most influential on the top, most influential on the bottom. Most influential on the top would just be your highest powered one. Same thing on the bottom, just what's highest powered. And so that's with all of these. So we're only going to be concerned about the most influential on the top and the bottom when we're looking at our limits as they approach infinity. Well, if we look only at what's highlighted here, that's a 3x cubed over an x. But then that reduces down to just a 3x squared. And we're looking at what happens as x gets really, really big. Well, if you put in a really big number and square it and times it by 3, and you keep putting in bigger and bigger numbers, it goes off to something really big. So we would say, in other words, there is no horizontal asymptote because as you go to the right, it goes up forever, approaching positive infinity. When we look at the next one here, the most influential over the most influential. You notice this one here again reduces just like the last one. Here your x cubes reduce, and it drops down to just a 3/5. No variables left, so as x approaches infinity, as x gets really, really big, it has no effect on this because there's no x's left. So in that case, we're going to level out at a height of 3/5. So your horizontal asymptote is 3/5. We're going to do the same type of thing down here at the bottom. Most influential over most influential. Once again, it would reduce, and we would get this. Now, as x gets really, really big, it causes the bottom to get big. And 3 over a really big number means it gets close to 0. So in this case, we would have a horizontal asymptote of y equals 0. Because 3 over something really, really big is really, really small, close to 0. So we need to go ahead and kind of generalize this. Whenever the degree of the numerator is greater than, or I mean less than, the degree of the denominator, you get a horizontal asymptote of 0. Whenever the degree of the numerator is equal to the degree of the denominator, the variables drop and you're just left with numbers. And it would be y equaling whatever those numbers were. Whenever your degree of your numerator is greater than the degree of your denominator, there is no horizontal asymptote. However, there is an oblique asymptote, and we'll be talking about that later.